In this video, I will be showing you an example of a PLC project. With this project, it is aimed to build a spot welding station. So let me briefly tell you about how it works. We have a conveyor to begin with, right? And it has the product on it. So when someone presses the start button, the conveyor starts running, and as it gets closer to the station, it paces with a cylinder stopper. And this is constantly up because it has a single acted valve. Namely, you give energy to move this from one side to the opposite side, but then again, you don't have to give energy again to move it back to its original position. So you can think of it like a spring-loaded system, right? This is constantly up unless we tell the otherwise. So yeah, and it stops the conveyor. Product now is in the station, and it needs to be fixed because there's going to be operation on it, so it needs to stay still. To achieve that, we have locating pins that goes up into the production holes that is on the product, and we also have clamps that is clutching the product from the edges. So from now on, the 6-axis industrial robot takes over the operation to start the spot welding process. It has a welding gun as a tool, obviously, and after the robot is finished its job, and if everything is okay, now locating pins goes down, clamps are open, the stopper also goes down with the signal received from the PLC, and conveyor starts running again to deliver the product. So this is basically it. Now we can go through the program in TIA Portal. Starting with the main operation block, here I recall the function data blocks. Each checks a specific operation, so this is actually where you built the most recently. I've divided this operation into 4 sections, and we're going to take a closer look to each of them, but right now I'm going to start with the automated sequence. Also, an important notation is that you should always start with that because this is like the skeleton of the project. First 3 lines don't contribute to the project anyhow, they're just there to make things easier. Imagine you have 20 locating pins and you want them all up. So every time you need to use them, you have to put separate context for each of them, and that will make everything complicated. Cycle starts from here, from network 5, as the start button is pressed. So I've used the states machine logic in this ladder diagram. It's basically you assign random numbers to particular steps, and in that way you make sure the next step isn't computing before the initial step is over, and that prevents time overlapping for outputs. And I use the positive edge trigger for the start button. It prevents the machine from starting another cycle automatically if someone holds the button. The first step, or step 0, checks if the machine is ready to operate, and then it jumps into step 100 where the conveyor stops and the product has arrived at the station. In step 200, locating pins go up to lock the product into the place, and the memory bit checks for all the pins if their input sensors are aligned. Step 300 is where the clamps are closed. Within the first milliseconds of clamping, there may occur a mechanical stress between the product and the clamps, and the signal may ripple. So to make sure if the incoming signal is constant, I put a timer on. In step 400, PLC transfers the operation to the robot and the welding gun. So this is where our PLC gets rest, and we'll use this as a trigger in another function block. After welding is finished and if everything went flawlessly and if these conditions is satisfied, then we move to the step 500. The clamps and locating pins have single active valves, unlike the cylinder stopper. So from this point, it's kind of like repeating the process backwards. Step 700 is for cylinder stopper to go down. Step 750 runs the conveyor again to deliver the product. There is also a trick here called tail end. Sometimes when the part is outside the sensor's detection area, a small part of it can be still in the station and is about to leave, but not completely. To overcome this, it is suggested to put a timer on. Now we're on to the next function block that is designed for welding. As we remembered from the previous one, the memory bit Step 400 will be the trigger for this operation. Here again, before the operation begins, the system verifies that all physical conditions are met, like safety loop is okay, locating pins are up, clamps are closed, and the robot is in home position. It also checks the weld quality, which I'm going to refer in a minute. Network 2 acts as the final handshake, so if the safety bit is okay, if the area is clear to weld, and if the robot is asking for permission to start welding, then push the current. Network 3 works as a quality control center and checks if the welding quality is okay. So if there is 2 faulty welds in a row, it sets a quality error flag and automatically blocks network 1 and stops production. This function constantly tries to overcome this value to set the not okay signal. So if there is a 1 okay signal after 1 not okay signal, the counter goes back to 0 and starts counting again to catch 2 mistakes in a row. Network 4 lets the robot go from one welding point to another, whether the weld was successful or not, hence keep the cycle going. Best thing about state machine algorithm, it provides connecting initial step values directly to the output coils. I connected step 100 and 750 in parallel to run the conveyor. This means they don't have to be satisfied at the same time. It's either step 750 or 100, the conveyor starts running. Starting from step 200 to step 500, I need locating pins to be set up. For this purpose, I've used in-range data block. Well, the clamp close bit has a shorter cycle time compared to the pins up bit, so instead of using in-range block, I've just connected the 2 steps that it needs to be operating in parallel, and same for the cylinder stopper. Since the locating pins and clamps have single-acted valve, unlike the cylinder stopper, we need to have also output coils for reverse operations. But the logic stays the same. I'm using 2 in-range blocks in parallel because I need to energize the coil in 2 different time ranges. As the final section, I have safety function block. You can see there are a bunch of open contacts here connected in series. They get energized by the industrial safety equipments. Also in the field, they must be always connected in normally closed configuration. We get this general safety bit as a result, and we put it basically in front of every output coil. Back into the main block, you can arrange or check to make sure they are in the right order. I will say safety is on top, and see you in the next video where I will be possibly doing the HMI panel of this project. Thank you for watching.